Relativity. The very mention of the word strikes fear into the minds of those who don't understand the concept, that is, most people. However, while Einstein's ideas are profound and somewhat counterintuitive, they are actually very simple to understand, if you can follow the logic through without being misled. And this is what I shall try to do in this video, the first in a series where I'll eventually attempt to derive all of the fundamental laws of modern physics in this way. Einstein built his theory of special relativity on two postulates, fundamental assumptions that he derived everything else from. The first is Galileo's good old-fashioned principle of relativity. The laws of physics are the same in every inertial frame of reference, i.e., to the point of view of an observer moving at a constant velocity, it is impossible for them to tell that they are moving. Therefore, special relativity only applies in the special case of an inertial frame moving uniformly. Accelerating frames require general relativity, which is much more complicated. But we won't be bogged down in that, at least not for now. Let's take a closer look at different frames of reference. Imagine a tank driving along a road. From the frame of reference of the road, the tank is moving with a constant velocity. Let's call it u. However, for the tank driver, the tank is stationary and the road is moving backwards with velocity minus u. Both of these points of view are valid inertial frames. Now suppose the tank fires a shell with velocity v relative to the tank. Of course, to someone standing by the road, the shell appears to have velocity u plus v. Keep this thought in mind. Now, the second postulate is a bit more interesting. The speed of light is the same in every inertial frame. In the late 1800s, it was thought that light waves travelled through something called the luminiferous ether. Just like water waves need water to move through. In 1887, two American scientists, Albert Michelson and Edward Morley, attempted to measure the ether wind as the Earth moved through the ether. Their apparatus looked like this, with two arms, one parallel to the ether wind and the other perpendicular to it. They expected the light sent along the parallel arm to be delayed by the ether wind, causing destructive interference between the two beams. However, the light always took the same time to travel down both arms. There was no ether wind, which led Einstein to introduce his radical second postulate, which has some interesting consequences. Our tank's gun has now been upgraded to a big scary laser. Again, when the laser fires, the light travels at velocity c, the speed of light, relative to the tank. However, from our observer on the ground, the speed observed is not u plus c, it is still just c. Think about that for a few seconds. Now, it's time to talk about, well, time. In Einstein's thought experiments, time is measured with a light clock, which ticks when a particle of light bounces off one of these mirrors. We'll suppose that the speed of light is very slow, and therefore the clock ticks every second. Let's set one of these clocks in motion. Inside its own frame of reference, the clock still ticks every second. However, from outside, the light has to take a longer diagonal path. Since the light must still travel this increased distance at the same speed, it must take more time. Therefore, time on a moving object appears to slow down, an effect known as time dilation. Simultaneous events can even be separated by time dilation. Here, a pulse of light is sent to sensors on both ends of a moving train. From inside the train, light takes the same time to reach both sensors, so they activate simultaneously. But from outside, the light gets to the back sensor long before it can catch up to the front sensor. The person on board our tank has a slower clock, but he still has to measure the speed of light to be the same. Otherwise he could tell that he was moving. Since speed equals distance divided by time, a longer time taken must also mean a shorter distance for the light to travel to measure the same speed. So objects also become shorter as they approach light speed. This is called length contraction. The consequences of special relativity are very strange, but they have been tested by experiment. GPS satellites need to correct for time dilation to allow their measurements to be accurate. Also, remember the principle of relativity. Not only does our tank appear to get shorter and has slower time from the outside, an external observer also becomes thinner and has slower time, seen from inside the tank. There is one final consequence of special relativity. Einstein's most famous equation, E equals mc squared. But that shall have to wait till a later video. Until then, thank you very much for watching, and I will see you again next time. Goodbye.